Picture yourself standing on a beach at night, counting grains of sand. Now imagine that each grain represents an entire galaxy like our Milky Way, swirling with hundreds of billions of stars. Even if you counted every grain on every beach on Earth, you still wouldn't come close to the number of galaxies in our observable universe. The true scale of existence is so staggering that our minds literally cannot comprehend it. But today, we're going to try. We'll journey from our cosmic neighborhood to the very edge of everything we can see. You will discover just how impossibly vast our universe really is compared to our home galaxy. If you're fascinated by the mind-blowing scale of our cosmos and want to explore more incredible discoveries about our universe, make sure to subscribe to this channel and hit the like button. Now let's begin. Let's start close to home with our Milky Way galaxy, a cosmic island containing somewhere between 200 and 400 billion stars. From our vantage point on Earth, about 26,000 light-years from the galactic center, we see it edge on as that beautiful band of light stretching across the night sky. But the Milky Way is far more than just a pretty sight. It's a vast spiral disk roughly 100,000 light-years across and about 1,000 light-years thick, with spiral arms that wind outward like cosmic pinwheels. The European Space Agency's Gaia mission, launched in 2013, has revolutionized our understanding of our galaxy's structure. By precisely measuring the positions and motions of over 1.8 billion stars, Gaia has created the most detailed three-dimensional map of the Milky Way ever made. This incredible spacecraft has revealed that our galaxy isn't a perfect spiral. It's actually warped like a potato chip, with the outer edges bent upward on one side and downward on the other. Scientists believe this warping comes from gravitational interactions with smaller galaxies that have passed close by or even collided with ours in the distant past. At the heart of our galaxy lurks Sagittarius A star, a supermassive black hole with a mass 4 million times greater than our Sun. The Event Horizon Telescope collaboration made history in 2022 when they released the first image of this cosmic monster's shadow. Surrounding this black hole is a chaotic region where stars whip around at speeds of thousands of kilometers per second. The closest stars to the black hole complete their orbits in just a few years, compared to our Sun's leisurely 230 million-year journey around the galactic center. But here's where things get interesting. Our Milky Way, as enormous as it is, represents just one galaxy among trillions. The latest estimates from observations by the Hubble Space Telescope and other instruments suggest there are at least 2 trillion galaxies in the observable universe. Let that sink in for a moment. 2 trillion. That's 2 followed by 12 zeros. If you could visit one galaxy every second, it would take you over 63,000 years to see them all, and that's without stopping for lunch. These galaxies come in a stunning variety of shapes and sizes. There are spiral galaxies like our own, with their elegant rotating arms, elliptical galaxies that look like cosmic footballs containing mostly older stars and very little gas or dust, irregular galaxies with no defined shape, often distorted by gravitational interactions with their neighbors. And then there are the true monsters, giant elliptical galaxies that can contain over 1 trillion stars and stretch across millions of light-years. The nearest major galaxy to us is Andromeda, officially known as M31, located about 2.5 million light-years away. When you look at Andromeda with the naked eye, yes, you can actually see it on a clear, dark night. The light hitting your retina left that galaxy when our earliest human ancestors were just beginning to walk upright. Andromeda is slightly larger than the Milky Way, containing roughly 1 trillion stars, and it's heading straight for us at about 110 kilometers per second. Don't panic though, this cosmic collision won't happen for another 4 to 5 billion years. When it does, the two galaxies will dance around each other in a gravitational ballet lasting billions more years before eventually merging into a single, giant, elliptical galaxy. Some astronomers have already nicknamed this future merged galaxy Milkdromeda or Milkomeda. Despite the dramatic name, collision, very few, if any, stars will actually collide. The spaces between stars are so vast that the two galaxies will pass through each other like ghosts. The James Webb Space Telescope, launched on Christmas Day 2021, has pushed our vision deeper into space and further back in time than ever before. In July 2022, NASA released Webb's first deep field image, showing thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. Some of these galaxies are so distant that we're seeing them as they were over 13 billion years ago, when the universe was less than 1 billion years old. These ancient galaxies look nothing like the majestic spirals and ellipticals we see nearby. They're smaller, more chaotic, still in the process of forming. Webb has spotted galaxies that existed just a few 100 million years after the Big Bang, pushing back the frontier of when we thought the first galaxies could form. Some of these early galaxies are surprisingly massive and mature, challenging our models of how quickly structures could assemble in the early universe. But galaxies don't exist in isolation. They're organized into a vast cosmic web of clusters, superclusters, and enormous voids. Our Milky Way is part of a collection of more than 50 galaxies called the Local Group, which spans about 10 million light-years. The Local Group is dominated by 3 large spiral galaxies, the Milky Way, Andromeda, and the Triangulum Galaxy, M33. The rest are smaller dwarf galaxies, many of which orbit the larger galaxies like cosmic satellites. The large and small Magellanic Clouds, visible from the southern hemisphere, are the most famous of the Milky Way's satellite galaxies. These irregular dwarf galaxies are slowly being torn apart by our galaxy's gravity, leaving behind streams of gas and stars that trace their orbital paths. The Gaia mission has discovered numerous other stellar streams crisscrossing our galaxy, ghostly remnants of smaller galaxies that ventured too close and were shredded by tidal forces. Zooming out further, our Local Group is itself just a tiny part of the Virgo Supercluster, a collection of over 100 galaxy groups and clusters sprawling across 110 million light-years. At the heart of this supercluster lies the Virgo cluster, containing over 1,300 galaxies packed into a region just 15 million light-years across. The gravitational pull of all this matter is so strong that it's affecting the motion of our entire Local Group, pulling us toward it at about 600 kilometers per second. But even superclusters aren't the largest structures in the universe. In 2014, astronomers announced the discovery of the Laniakea supercluster, Hawaiian for immense heaven, which contains the mass of 100 million billion suns spread across 520 million light-years. Our Virgo supercluster is just one lobe of this even larger structure. The discovery of Laniakea revolutionized our understanding of our cosmic address. We're not just in the Milky Way, in the Local Group, in the Virgo supercluster. We're in a specific location within an even grander structure that's being pulled toward a gravitational anomaly called the Great Attractor. Speaking of our galaxy's mysteries, if you want to explore what lies at the heart of our Milky Way in stunning detail, check out my video, Journey to the Center of the Milky Way, where we dive deep into the chaotic region around our galaxy's supermassive black hole. The link is in the description below and pinned on the comments. Now let's continue our cosmic journey outward. The cosmic web becomes visible when we map the locations of millions of galaxies. This vast network looks remarkably like neural networks in the brain or the intricate patterns of spider webs, with dense filaments of galaxies separated by enormous voids. The largest of these voids can span hundreds of millions of light-years, containing almost no galaxies at all. It's as if the universe has bubbles blown into its structure, with galaxies congregating on the bubble walls. The Sloan Digital Sky Survey, one of the most ambitious astronomical surveys ever undertaken, has mapped over 3 million cosmic objects, revealing the cosmic web in unprecedented detail. The survey uses a dedicated 2.5-meter telescope in New Mexico that has been systematically photographing the sky since 2000. The data has revealed walls, filaments, and voids that stretch across billions of light-years, showing us that the universe has structure on scales that dwarf anything we previously imagined. One of the most mind-bending discoveries is the Hercules Corona Borealis Great Wall, a vast collection of galaxies that spans approximately 10 billion light-years, more than 1/10 the diameter of the observable universe. This structure is so large that it challenges our understanding of how the universe evolved. According to current models, gravity shouldn't have had enough time since the Big Bang to pull matter together into such enormous structures. Yet there it is, forcing cosmologists to reconsider their theories. The observable universe, everything we can possibly see, extends about 46.5 billion light-years in every direction from Earth. You might wonder how we can see 46 billion light-years away when the universe is only 13.8 billion years old. The answer lies in cosmic expansion. While light from the most distant galaxies has been traveling toward us for over 13 billion years, the space between us and those galaxies has been stretching the entire time. The galaxies that emitted the light we're now seeing are now much farther away than they were when the light began its journey. This brings us to one of the most profound realizations in cosmology. The observable universe is not the entire universe. It's simply the sphere around us from which light has had time to reach us since the Big Bang. Beyond this cosmic horizon, there are presumably more galaxies, more clusters, more of everything. We just can't see them because their light hasn't had time to reach us yet. The actual universe might be infinite in extent, or it might curve back on itself in higher dimensions. We simply don't know. The cosmic microwave background, or CMB, gives us a baby picture of the universe from when it was only 380,000 years old. The Planck satellite, operated by the European Space Agency from 2009 to 2013, created the most detailed map ever made of this ancient light. The CMB shows us the universe before any stars or galaxies existed, when it was just a hot soup of particles beginning to cool down. The tiny temperature variations in the CMB, differences of just 1 part in 100,000, were the seeds that gravity would amplify over billions of years into the cosmic web we see today. What's truly remarkable is how uniform the CMB is across the sky. Regions that we see in opposite directions, separated by the full width of the observable universe, have nearly identical temperatures. This suggests that these regions were once in contact, able to exchange heat and reach equilibrium. This observation led to the theory of cosmic inflation, a period of exponential expansion in the universe's first fraction of a second that stretched tiny regions to enormous sizes. Recent observations have revealed that the universe's expansion is not just continuing, it's accelerating. In 1998, 2 independent teams studying distant supernovae made this shocking discovery, which earned them the 2011 Nobel Prize in Physics. Something is pushing galaxies apart faster and faster, and we call this mysterious force dark energy. It makes up about 68% of the universe's total energy density, yet we have no idea what it actually is. The implications of accelerating expansion are staggering. Galaxies that we can see today are moving away from us faster and faster. Eventually, they'll be receding so fast that their light can no longer reach us. In the far future, trillions of years from now, any civilization in our galaxy will look out and see only the galaxies of our local group. The rest of the universe will have disappeared beyond the cosmic horizon, leaving future astronomers with no evidence that anything exists beyond their local cluster of galaxies. The Hubble Space Telescope has been humanity's eye on the universe for over 3 decades, fundamentally changing our understanding of cosmic scales. One of its most famous observations is the Hubble Ultra Deep Field, where the telescope stared at a seemingly empty patch of sky for over 11 days. The resulting image revealed over 10,000 galaxies in an area of sky smaller than a grain of rice held at arm's length. If the entire sky contains a similar density of galaxies, there would be over 200 billion galaxies in the observable universe, though recent estimates suggest the number is actually much higher. The distances in space are so vast that we need special units to measure them. A light year, the distance light travels in 1 year, equals about 9.5 trillion kilometers. Our nearest star, Proxima Centauri, is 4.2 light-years away. The Milky Way is about 100,000 light-years across. Andromeda is 2.5 million light-years distant. The observable universe spans 93 billion light-years. These numbers are so large they become meaningless to our everyday experience. To put this in perspective, let's shrink things down. If we made the Earth the size of a grain of sand, the Sun would be a marble about 1 meter away. Neptune, the outermost major planet, would orbit 18 meters from our marble Sun, but Proxima Centauri would be another marble located 260 kilometers away, about the distance from New York City to Boston. On this scale, the Milky Way would be 6 million kilometers across, 16 times the actual distance from Earth to the Moon. And the observable universe, it would still be larger than our actual solar system. The sheer emptiness of space is perhaps even more mind-boggling than its size. If you were to randomly place yourself somewhere in the universe, the odds of being inside a galaxy are incredibly small. Most of the universe is void, vast expanses of nearly empty space containing only a few hydrogen atoms per cubic meter. Even within galaxies, the distances between stars are enormous. If stars were the size of grains of sand, they would be separated by kilometers of empty space. Space is so empty that when galaxies collide, almost no stars actually crash into each other. This cosmic emptiness extends to our own solar system. If you add up all the planets, moons, asteroids, and comets in our solar system, they make up less than 0.2% of the solar system's total mass. The Sun contains 99.8%. And the solar system itself is mostly empty space. If you were to drive a car at highway speeds from the Sun to Neptune, it would take over 4,000 years of non-stop driving, yet our entire solar system is just a microscopic speck within the Milky Way. Dark matter adds another layer of mystery to cosmic scales. We can't see it directly, but we know it's there from its gravitational effects. When astronomers measure how fast stars orbit within galaxies, they find that galaxies must contain far more mass than we can see. The visible matter, stars, gas, and dust, makes up only about 15% of a galaxy's total mass. The other 85% is dark matter, forming an invisible halo that extends far beyond the visible galaxy. The Vera Rubin Observatory, set to begin operations in 2024, will revolutionize our understanding of dark matter and the universe's structure. Named after the astronomer who provided crucial evidence for dark matter's existence, this telescope will photograph the entire visible sky every few nights. Over 10 years, it will catalogue billions of galaxies, creating a 3-dimensional map of the universe with unprecedented detail. This cosmic census will help us understand how dark matter shapes the cosmic web and how dark energy drives the universe's acceleration. Galaxy clusters, the largest gravitationally bound structures in the universe, showcase physics on mind-bending scales. The Coma cluster, located 320 million light-years away, contains over 1,000 galaxies swarming around each other like bees in a cosmic hive. The galaxies move so fast, up to thousands of kilometers per second, that the cluster should fly apart unless there's far more mass than we can see. This was one of the first clues that dark matter exists. Between the galaxies in clusters lurks the intracluster medium, gas heated to temperatures of millions of degrees. This gas, invisible to optical telescopes but glowing brightly in X-rays, contains more ordinary matter than all the galaxies in the cluster combined. The Chandra X-ray Observatory and XMM Newton have revealed this hidden universe of hot gas, showing us cosmic collisions where clusters merge at speeds of millions of kilometers per hour, creating shock waves larger than entire galaxies. The Bullet cluster provides the most dramatic evidence for dark matter's existence. This cosmic crash site shows two galaxy clusters that collided around 150 million years ago. X-ray images reveal that the hot gas from the two clusters slowed down and bunched up during the collision, like two puddles of water splashing together. But gravitational lensing, the bending of light from background galaxies, shows that most of the mass sailed right through the collision. This invisible mass is dark matter, which doesn't interact with itself or ordinary matter except through gravity. Gravitational lensing itself reveals the universe's structure in stunning ways. Massive objects like galaxy clusters bend space-time, causing light from more distant galaxies to curve around them. This creates distorted, magnified images of background galaxies, sometimes stretching them into long arcs or even complete circles called Einstein rings. The Hubble Space Telescope has captured hundreds of these cosmic lenses, which act like natural telescopes, magnifying galaxies too distant and faint to see otherwise. The most distant galaxy ever confirmed, JD's GS Z13-0, was discovered by the James Webb Space Telescope in 2022. We see this galaxy as it was just 325 million years after the Big Bang, when the universe was only 2% of its current age. The light from this ancient galaxy has been traveling toward us for over 13.4 billion years, stretched by cosmic expansion until its ultraviolet light became infrared radiation that only Webb's sensitive instruments could detect. These early galaxies challenge our understanding of cosmic evolution. They're smaller than modern galaxies, typically only 1% the mass of the Milky Way, but they're forming stars at prodigious rates. Some create new stars hundreds of times faster than our galaxy does today. They're also surprisingly enriched with heavy elements, suggesting that the first generation of stars lived fast and died young, seeding space with the elements necessary for planets and life. The cosmic distance ladder helps astronomers measure these vast scales. For nearby stars, we use parallax, the apparent shift in a star's position as Earth orbits the Sun. For more distant objects, we use standard candles, objects with known brightness like Cepheid variables, and type Ia supernovae. Each rung of the ladder depends on the previous one, building up from distances we can measure directly to the edge of the observable universe. Recently, tension has emerged in measurements of the universe's expansion rate, known as the Hubble constant. Measurements using the cosmic microwave background give a value of about 67 kilometers per second per megaparsec, while measurements using supernovae give about 73. This discrepancy, called the Hubble tension, might indicate new physics beyond our current models. Perhaps dark energy changes over time, or maybe there's an additional form of matter or energy we haven't discovered yet. Time itself becomes strange on cosmic scales. Because light takes time to travel, looking into space means looking back in time. When you see the sun, you're seeing it as it was 8 minutes ago. When you look at the stars in Orion's belt, you're seeing light that left those stars hundreds of years ago. The bowl of the Big Dipper shows you light from about 80 years ago, while the handle stretches back over 200 years. Every night, sky is a patchwork of different times, a cosmic history book written in light. This cosmic time machine extends to the edge of the observable universe. The most distant galaxies we can see appear as they were when the universe was young. We can't see what they look like now. That light hasn't reached us yet and never will due to cosmic expansion. Those ancient galaxies have evolved for over 13 billion years since emitting the light we now detect. They've merged with other galaxies, formed new stars, and transformed in ways we can only imagine. The concept of cosmic inflation helps explain why the universe looks the way it does on the largest scales. In the first trillionth of a second after the Big Bang, the universe expanded faster than light. Yes, space itself can expand faster than light travels through it. This period of inflation stretched microscopic quantum fluctuations to cosmic scales, seeding the variations that would eventually grow into the cosmic web. Without inflation, the universe would be boringly smooth, with no galaxies, stars, or planets. Alan Guth proposed inflation in 1980 to solve several puzzles in cosmology. Why is the universe so flat? Why is the cosmic microwave background so uniform? Why don't we see magnetic monopoles? Inflation elegantly answers all these questions by proposing that our observable universe originated from a tiny patch of space that was stretched to enormous size. It's like zooming in on a curved basketball until a small patch looks perfectly flat. The multiverse, the idea that our universe is one of many, emerges naturally from inflation theory. If inflation can happen once, it can happen many times, creating pocket universes like bubbles in an eternal foam. Each universe might have different physical laws, different constants of nature, even different numbers of dimensions. Our universe, with its particular set of laws that allow atoms, stars, and life, might be just one of an infinite variety. This raises profound questions about our cosmic significance. If there are infinite universes with every possible set of physical laws, is there anything special about ours? The anthropic principle suggests we naturally find ourselves in a universe compatible with our existence. We couldn't observe a universe where atoms can't form or stars can't shine. But this feels unsatisfying to many scientists who hope to find deeper reasons why our universe has the properties it does. Cosmic voids represent another extreme of scale. These vast empty regions containing few or no galaxies can span hundreds of millions of light-years. The largest known void, the KBC void, might be 2 billion light-years across, so large that our entire local group might be inside it. Living inside a cosmic void could explain some puzzling observations about the universe's expansion rate in our neighborhood. The Boss Great Wall, discovered by the Baryon Oscillation Spectroscopic Survey, stretches across 1 billion light-years, containing thousands of galaxies arranged in a cosmic lattice. These enormous structures form along the intersections of dark matter filaments, where gravity has had billions of years to concentrate matter. They represent the universe's skeletal structure, the cosmic bones around which galaxies cluster. Computer simulations like the Millennium Simulation and the Illustris project have recreated the universe's evolution in stunning detail. Starting from the tiny fluctuations seen in the cosmic microwave background, these simulations use supercomputers to calculate how gravity pulls matter together over billions of years. The results look remarkably like the actual universe, with a cosmic web of filaments and voids, clusters and superclusters forming naturally from the laws of physics. These simulations reveal that galaxy formation is a violent process. Galaxies grow by cannibalizing their neighbors, with larger galaxies consuming smaller ones in cosmic feeding frenzies. Our own Milky Way shows evidence of past meals, streams of stars marking the remains of dwarf galaxies it has devoured. The Sagittarius dwarf spheroidal galaxy is being eaten right now, its stars being stripped away and incorporated into our galaxy's halo. The future of the universe depends on dark energy's nature. If dark energy remains constant, the universe will expand forever, growing colder and emptier. Galaxies outside our local group will eventually disappear beyond the cosmic horizon. Stars will burn out, black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy called heat death. This cheerful scenario plays out over timescales so vast they make the current age of the universe seem like an eye blink. But dark energy might not be constant. If it strengthens over time, we could face the Big Rip, a scenario where the expansion accelerates so much that it tears apart galaxies, solar systems, and eventually atoms themselves. Current observations suggest this won't happen for at least 20 billion years, if at all. On the other hand, if dark energy weakens or reverses, the universe might eventually stop expanding and collapse in a big crunch, potentially bouncing into a new Big Bang. The Perseus-Pisces supercluster, stretching across 300 million light-years, contains thousands of galaxies arranged in a cosmic chain. This structure is so large that its gravity affects the motion of our entire local group. We're falling toward it at about 300 kilometers per second, part of a cosmic flow that involves millions of galaxies streaming through space together. The Great Attractor remains one of the universe's mysteries. This gravitational anomaly, hidden behind the disk of our own galaxy, pulls hundreds of thousands of galaxies toward it. Recent observations suggest it's associated with the Norma cluster and the larger Laniakea supercluster structure. The entire region contains the mass of tens of thousands of galaxies, creating a gravitational well that affects cosmic motion across hundreds of millions of light-years. Radio telescopes have revealed a hidden universe invisible to optical instruments. The square-kilometre array, currently under construction in Australia and South Africa, will be the world's largest radio telescope. It will map billions of galaxies using the radio waves emitted by hydrogen gas, revealing the cosmic web structure in unprecedented detail. This hydrogen, the universe's most abundant element, traces cosmic structure like a vast, three-dimensional spider web. The Atacama Large Millimeter Array in Chile's high desert observes the universe in wavelengths between radio and infrared. ALMA has peered through cosmic dust to witness star formation in distant galaxies, revealing stellar nurseries where new suns are born. It has detected complex organic molecules in space and observed protoplanetary disks where new worlds are forming. Each observation adds another piece to our understanding of how galaxies evolve across cosmic time. Quasars, the blazing hearts of distant galaxies, serve as cosmic lighthouses. These supermassive black holes, actively feeding on surrounding gas, can outshine entire galaxies. The most distant known quasar, J0313-1806, shines from when the universe was only 670 million years old. Its black hole, with a mass 1.6 billion times our Sun, challenges our understanding of how such massive objects could form so quickly after the Big Bang. The light from quasars, traveling for billions of years through space, encounters clouds of gas along the way. These clouds absorb specific wavelengths of light, creating what astronomers call the Lyman alpha forest, a series of absorption lines in quasar spectra that map the distribution of hydrogen across cosmic time. By studying these absorption patterns, we can trace how gas is distributed throughout the universe and how it has evolved over billions of years. Reionization represents a critical phase in cosmic history when the first stars and galaxies flooded the universe with ultraviolet light. Before this epoch, about 400 million years after the Big Bang, the universe was filled with neutral hydrogen that absorbed visible light, making the cosmos opaque. The first stars ionized this hydrogen, creating bubbles of transparency that grew and merged until the entire universe became transparent. The James Webb Space Telescope is witnessing this cosmic dawn, observing the earliest galaxies that lit up the universe. Fast radio bursts, brief, intense pulses of radio waves from distant galaxies, have emerged as a new cosmic mystery. These millisecond-long flashes release as much energy as the Sun emits in days or even years. The CHIME telescope in Canada and other radio observatories have detected hundreds of these bursts, some from galaxies billions of light-years away. Each burst carries information about all the matter it passed through on its journey, making them cosmic probes of the universe's structure. The South Pole Telescope and the Atacama Cosmology Telescope are mapping the cosmic microwave background with extraordinary precision. These observations reveal subtle patterns that tell us about the universe's composition, age, and ultimate fate. The measurements show that ordinary matter, the stuff of stars, planets, and people, makes up only about 5% of the universe's total energy. Dark matter accounts for 27%, and dark energy dominates at 68%. Galaxy morphology changes dramatically over cosmic time. When we look at galaxies billions of light-years away, we see them as they were billions of years ago. These ancient galaxies look different from modern ones. They're smaller, more irregular, forming stars more vigorously. The stately spiral and elliptical galaxies we see nearby are the mature products of billions of years of evolution, having grown through mergers and star formation. The Hubble sequence, created by Edwin Hubble in the 1920s, classifies galaxies by their appearance: spirals, barred spirals, ellipticals, and irregulars. But we now know this sequence doesn't represent an evolutionary track. Galaxies don't start as ellipticals and become spirals. Instead, spirals that merge often create ellipticals. The universe's gallery of galaxy shapes reflects different formation histories and environments. The cosmic noon about 10 billion years ago was when star formation peaked across the universe. Galaxies were forming stars 10 times faster than they do today. This era of cosmic fertility created most of the stars we see in the universe. Since then, star formation has steadily declined. Our Milky Way once formed stars prolifically, but now creates only a few new suns per year. The universe is slowly running out of the gas needed to make new stars. Metallicity, the abundance of elements heavier than hydrogen and helium, serves as a cosmic clock. The first stars contained only hydrogen and helium from the Big Bang. When these stars exploded as supernovae, they seeded space with heavier elements like carbon, oxygen, and iron. Each subsequent generation of stars incorporated these metals, becoming progressively enriched. By measuring a star's metallicity, astronomers can estimate its age and understand its place in cosmic history. Our Sun is a third-generation star, formed from gas enriched by at least 2 previous generations of stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stars that lived and died before our solar system existed. You are literally made of stardust assembled from atoms created in stellar furnaces billions of years ago. Every element in your body except hydrogen has cycled through at least one star's core. The cosmic web's structure emerged from quantum fluctuations during inflation. These microscopic variations, stretched to cosmic scales, created regions slightly denser than average. Gravity amplified these tiny differences over billions of years. Denser regions attracted more matter, becoming denser still, eventually collapsing into the first stars and galaxies. The pattern of fluctuations imprinted on the cosmic microwave background predicted exactly the cosmic web we see today. Baryon acoustic oscillations, subtle ripples in the distribution of galaxies, provide a cosmic ruler for measuring distances across the universe. These patterns originated as sound waves in the hot plasma of the early universe. When the universe became transparent at 380,000 years old, these waves froze in place, creating a characteristic length scale that we can still measure today. This cosmic yardstick helps us map the universe's expansion history with remarkable precision. The cosmic assembly, near-infrared, deep, extragalactic. Legacy Survey, or CANDELS, represents one of the largest Hubble Space Telescope projects. It imaged over 250,000 galaxies in deep exposures of the sky, revealing galaxies as they appeared when the universe was only a few 100 million years old. These observations show us cosmic evolution in action, tracking how galaxies grew and changed over 13 billion years. Galaxy Zoo, a citizen science project launched in 2007, enlisted hundreds of thousands of volunteers to classify over 900,000 galaxies. This crowdsourced science revealed rare galaxy types and discovered new phenomena like green P galaxies, small star-forming galaxies glowing bright green due to ionized oxygen emission. The project demonstrated that human pattern recognition, combined with massive public participation, could unlock cosmic discoveries that computers alone might miss. The Spitzer Space Telescope, operating from 2003 to 2020, revealed the infrared universe. Infrared light penetrates cosmic dust that blocks visible light, allowing Spitzer to peer into star-forming regions and see galaxies hidden behind dust clouds. It mapped the distribution of stellar mass across the universe, showing that much of the universe's star formation occurs shrouded in dust, invisible to optical telescopes. The intergalactic medium, the tenuous gas filling the space between galaxies, contains more ordinary matter than all the galaxies combined. This gas, heated to millions of degrees, glows faintly in ultraviolet and X-ray light. It forms the cosmic web's filaments, flowing along dark matter highways between galaxy clusters. When galaxies form, they pull this gas inward, feeding their star formation. Understanding this gas reservoir helps explain how galaxies grow and evolve over cosmic time. Supermassive black holes lurk at the centers of nearly all large galaxies, with masses ranging from millions to billions of times the Sun's mass. The relationship between a galaxy's central black hole and its total mass suggests a deep connection between galaxy evolution and black hole growth. Somehow, these cosmic monsters and their host galaxies co-evolve, with each influencing the other's development. When black holes feed actively as quasars, their energy output can blow gas out of the galaxy, shutting down star formation. The M87 galaxy, located 55 million light-years away in the Virgo cluster, hosts one of the most massive black holes known, 6.5 billion solar masses. The Event Horizon Telescope captured the first image of this black hole's shadow in 2019, showing the glowing ring of hot gas swirling around it. This groundbreaking image confirmed Einstein's predictions about extreme space-time curvature and gave humanity its first direct view of a black hole's event horizon. Active galactic nuclei powered by supermassive black holes can launch jets of plasma at nearly the speed of light. These jets extend for millions of light-years far beyond the visible galaxy, pumping energy into the intergalactic medium. The most powerful jets have carved cavities in the hot gas surrounding galaxy clusters, creating cosmic bubbles larger than our entire Milky Way. This energy feedback regulates galaxy growth, preventing the largest galaxies from consuming all available gas. Ultra-diffuse galaxies challenge our understanding of galaxy formation. These ghostly objects are as large as the Milky Way but contain only 1% as many stars, making them barely visible against the sky. Some contain almost no dark matter, while others are dominated by it. Their existence suggests that galaxy formation can follow many different paths, producing a stunning diversity of cosmic structures. The local void, a region of space about 150 million light-years across containing few galaxies, sits next to our cosmic neighborhood. We're located on the edge of this void, in a relatively dense region. The void's gravitational deficit pushes galaxies away, contributing to our local motion through space. Living on a void's edge might explain why local measurements of cosmic expansion differ slightly from the average rate predicted by cosmic microwave background observations. Dwarf galaxies, though small, outnumber giant galaxies by at least 10 to 1. Most contain fewer than 1 billion stars compared to the Milky Way's 2 to 400 billion. Despite their small size, dwarfs play crucial roles in cosmic evolution. They serve as building blocks for larger galaxies, and studying them helps us understand how the first galaxies formed. The smallest known galaxy, Segue 2, contains only about 1,000 stars but has taught us valuable lessons about dark matter and galaxy formation. Tidal dwarf galaxies form from debris during galactic collisions. When two galaxies merge, their gravitational interaction flings gas and stars outward in long streamers. Sometimes these tidal tails contain enough material to collapse under their own gravity, forming new dwarf galaxies. These recycled galaxies provide natural laboratories for studying star formation in unusual environments. The cosmic distance scale relies on overlapping measurement techniques, each calibrated against the others. For the nearest stars, we use geometric parallax from Earth's orbit. For nearby galaxies, we observe Cepheid variable stars whose brightness varies predictably with their period. For more distant galaxies, we use Type Ia supernovae as standard candles, and for the most distant objects, we measure redshift, how much cosmic expansion has stretched their light toward longer wavelengths. Redshift serves as a cosmic speedometer and clock combined. When a galaxy moves away from us, its light stretches to longer, redder wavelengths. The faster the recession, the greater the redshift. Objects with redshift greater than 7 show us the universe when it was less than 1 billion years old. The most distant confirmed object has a redshift of 13.2, meaning we see it as it was just 325 million years after the Big Bang. Cosmic expansion doesn't mean galaxies are moving through space away from each other. It means space itself is expanding, carrying galaxies along like raisins in rising bread dough. This distinction becomes crucial when understanding how light travels across the universe. A photon emitted from a distant galaxy fights against cosmic expansion for billions of years, its wavelength stretching as space expands around it. By the time it reaches us, that ancient ultraviolet light has been transformed into infrared radiation. The cosmological principle states that the universe is homogeneous and isotropic on large scales. It looks roughly the same in all directions and at all locations. This principle, supported by observations of the cosmic microwave background and galaxy surveys, implies that there's nothing special about our location in the universe. We're not at the center. In fact, in an infinite or unbounded universe, there is no center. Cosmic strings, if they exist, would be one-dimensional defects in space-time left over from the early universe. These incredibly dense, infinitely thin threads would stretch across the cosmos, possibly explaining some large-scale structures. While they remain hypothetical, observations continue to search for their signatures, peculiar distortions in the cosmic microwave background or distinctive gravitational lensing patterns. Their discovery would revolutionize our understanding of the universe's earliest moments. The zone of avoidance, hidden behind our galaxy's disk, conceals about 10% of the sky from our view. Dust and stars in the Milky Way's plane block light from distant galaxies in these directions. Radio and infrared observations can partially penetrate this obscuration, revealing hidden galaxy clusters and structures. The Great Attractor lies partially in this zone, making it challenging to study directly. The cosmic neutrino background, if we could detect it, would show us the universe at just 1 second old. These ghostly particles decoupled from matter even earlier than photons, carrying pristine information about conditions when the universe was unimaginably hot and dense. Unlike the cosmic microwave background photons, these relic neutrinos have cooled to less than 2 degrees above absolute zero and are extraordinarily difficult to detect. Future experiments might finally capture these elusive messengers from the universe's first second. Gravitational waves offer an entirely new way to observe the cosmos. The LIGO and Virgo detectors have opened this new window, detecting ripples in space-time from colliding black holes and neutron stars. The planned LISA space mission will detect gravitational waves from supermassive black hole mergers across the universe. These observations don't rely on light, so they can reveal cosmic events completely invisible to traditional telescopes, including the universe's first black holes forming in the cosmic dawn. The Shapley supercluster, located 650 million light-years away, is the largest concentration of galaxies in our cosmic neighborhood. It contains over 8,000 galaxies and 25 massive clusters, with a total mass of 10 million billion suns. This enormous structure exerts a powerful gravitational pull on our local group and everything around it. Our entire cosmic neighborhood is streaming towards Shapley at about 600 kilometers per second. Cosmic filaments, the strands connecting galaxy clusters in the cosmic web, have recently been observed directly. The extremely hot, tenuous gas filling these filaments was predicted by simulations, but only confirmed in the 2010s using X-ray and microwave observations. These filaments, millions of light-years long, channel matter from voids into clusters, serving as the circulatory system of the cosmic web. The axis of evil, a tongue-in-cheek name for an unexpected alignment in cosmic microwave background fluctuations, has puzzled cosmologists since its discovery by the WMAP satellite. Large-scale temperature variations seem oddly aligned with the plane of our solar system, which should be completely random. While likely a statistical fluke, this alignment reminds us that cosmic observations still hold surprises that challenge our understanding. Einstein's general relativity has passed every observational test with flying colors. From the tiny deflection of starlight by the sun to gravitational waves from colliding black holes, every prediction has been confirmed. The theory tells us that space-time is curved by mass and energy, and this curvature guides the motion of matter and light. On cosmic scales, general relativity governs the evolution of the entire universe, from the Big Bang to the present day. But general relativity might break down at the universe's smallest scales or earliest moments. Quantum mechanics, our theory of the subatomic world, seems fundamentally incompatible with general relativity. Resolving this conflict requires a theory of quantum gravity that doesn't yet exist. String theory, loop quantum gravity, and other approaches attempt to unite these frameworks, potentially revealing new physics that becomes important in black holes or during the Big Bang. The Wilkinson Microwave Anisotropy Probe, or WMAP, operated from 2001 to 2010, mapping the cosmic microwave background with unprecedented precision. Its observations pinned down the universe's age at 13.8 billion years, determined its composition, and confirmed that space is geometrically flat. These measurements transformed cosmology from a data-poor field, making rough estimates into a precision science with parameters measured to better than a few % accuracy. Flat geometry means that parallel lines stay parallel forever. Space doesn't curve back on itself like a sphere or curve away like a saddle. This geometric flatness is remarkable because any deviation from perfect flatness would have been amplified enormously over cosmic history. The fact that we measure the universe to be flat to within 1% suggests it's probably exactly flat, possibly extending infinitely in all directions beyond our observable horizon. The fate of the universe depends on its geometry and composition. A closed universe curves back on itself and would eventually collapse. An open universe curves away and expands forever. A flat universe sits precisely on the boundary between these fates. With current observations showing flatness and accelerating expansion due to dark energy, the universe appears destined to expand eternally, growing colder and emptier as galaxies disappear beyond the cosmic horizon. Primordial nucleosynthesis, the formation of light elements in the Big Bang's first minutes, provides another cosmic ruler. The relative abundances of hydrogen, helium, and lithium depend on the universe's density and expansion rate during those early minutes. Observations of these abundances in ancient stars and gas clouds match theoretical predictions beautifully, confirming our understanding of the universe when it was just minutes old. The cosmic neutrino problem refers to the mismatch between observed and predicted neutrino properties. Neutrinos come in 3 types or flavors, and they oscillate between these flavors as they travel. These oscillations tell us that neutrinos have tiny but non-zero masses. The sum of these masses affects cosmic structure formation, leaving imprints on the distribution of galaxies. Current observations constrain this sum to less than 1/10 of an electron volt, extraordinarily light but not massless. Warm dark matter and cold dark matter represent different hypotheses about dark matter's nature. Cold dark matter moves slowly compared to light speed, allowing structures to form from the bottom up. Small objects first, which then merge into larger ones. Warm dark matter moves faster, preventing the smallest structures from forming. Observations of satellite galaxies around the Milky Way help distinguish between these scenarios, with current evidence favoring cold dark matter. Self-interacting dark matter proposes that dark matter particles can collide with each other, not just exert gravitational force. These interactions would smooth out the centers of dark matter halos, potentially solving puzzles about galaxy structure. The bullet cluster and similar cosmic collisions provide natural experiments to test this idea. So far, observations suggest dark matter is either completely collisionless or interacts only very weakly with itself. Fuzzy dark matter, composed of ultralight particles called axions, would behave like a quantum wave on galactic scales. This wave-like nature would prevent dark matter from clumping on small scales, potentially explaining why we don't see as many small satellite galaxies as simulations predict. The wave interference patterns might create observable signatures in how dark matter is distributed in galaxy centers, offering a way to test this exotic hypothesis. The Planck satellite's final data release in 2018 provided our most precise measurements of cosmic parameters. The mission mapped temperature variations in the cosmic microwave background to 1 part in a million, revealing the universe's baby picture in exquisite detail. These measurements tell us the universe's age, composition, geometry, and expansion history with remarkable accuracy, establishing a standard model of cosmology. Cosmic topology asks what shape the universe has on the largest scales. Even if space is geometrically flat locally, it might connect back on itself in clever ways, like how a flat sheet of paper can be rolled into a cylinder. If the universe has exotic topology, we might see multiple images of the same distant objects copied around the sky. Searches for such repeating patterns have found nothing, suggesting that if the universe does connect back on itself, it does so on scales larger than we can observe. The cold spot in the cosmic microwave background, a region about 10 degrees across that's slightly cooler than surrounding areas, has sparked debate since its discovery. Some scientists suggest it might be evidence for a supervoid, an especially empty region of space that light passes through on its way to us. Others wonder if it could indicate something more exotic, perhaps even a collision between our universe and another bubble universe. Most likely, it's just a statistical fluctuation, but it reminds us that cosmic mysteries remain. Galaxy rotation curves, measurements of how fast stars and gas orbit at different distances from galactic centers, provided the strongest early evidence for dark matter. Visible matter concentrates toward galaxy centers, so we'd expect orbital speeds to decrease with distance, like planets orbiting the Sun. Instead, rotation speeds remain constant far beyond the visible disk, implying vast halos of invisible matter. Vera Rubin's pioneering work measuring these curves in the 1970s convinced astronomers that dark matter must be real. Modified Newtonian dynamics, or MOND, attempts to explain galaxy rotation curves without dark matter by proposing that gravity behaves differently at extremely low accelerations. While EMOND successfully matches rotation curves for individual galaxies, it struggles with galaxy clusters, gravitational lensing, and cosmic structure formation. Most physicists favor dark matter because it explains observations across all scales with a single hypothesis, while MOND requires different modifications for different situations. The Vera C. Rubin Observatory, scheduled to begin operations in 2025, will photograph the entire southern sky every few nights for 10 years. This legacy survey of space and time will catalogue billions of galaxies, discover millions of asteroids, and monitor the sky for anything that changes or moves. The resulting data will help us map dark matter through gravitational lensing, trace the cosmic web's evolution, and potentially discover entirely new phenomena we haven't yet imagined. Baryon physics, the behavior of ordinary matter, plays a crucial role in galaxy formation despite making up only 5% of the universe. Gas cooling, star formation, supernova explosions, and black hole feedback all affect how galaxies grow and evolve. Modern cosmological simulations must include these complex processes to match observations. The interplay between dark matter providing gravitational scaffolding and baryons forming visible structures creates the rich diversity of galaxies we observe. The Euclid mission, launched by the European Space Agency in 2023, will map the geometry of the dark universe. By observing billions of galaxies and measuring how their shapes are distorted by gravitational lensing, Euclid will trace dark matter's distribution across 10 billion years of cosmic history. It will also measure how cosmic expansion has changed over time, constraining dark energy's properties and testing whether Einstein's gravity needs modification on cosmic scales. Cosmic voids aren't completely empty. They contain some galaxies, just far fewer than average regions. These void galaxies are interesting because they evolve in relative isolation, without the frequent mergers and interactions that affect galaxies in denser environments. Studying void galaxies helps us understand how environment shapes galaxy evolution. Some voids also show puzzling internal structure, with smaller voids nested inside larger ones like cosmic bubbles within bubbles. The dipole repeller, discovered through analysis of galaxy motions in 2017, is a vast underdense region that pushes our local group away through its gravitational deficit. While the Shapley supercluster pulls us from one direction, the dipole repeller pushes from the opposite side. Together, these structures create our peculiar velocity, our motion relative to the cosmic microwave background's rest frame. We're being squeezed through space at about 630 kilometers per second by this push-pull dynamic. Cosmic flows, large-scale motions of galaxies, reveal mass concentrations too distant to see directly. By measuring how galaxies move relative to the smooth cosmic expansion, astronomers map the gravitational landscape across hundreds of millions of light-years. These observations have revealed unexpected concentrations of mass and shown that the universe's matter distribution is clumpier than simple models predict. The end of greatness refers to the scale, about 300 million light-years, beyond which the universe becomes statistically uniform. Below this scale, we see rich structure, galaxies, clusters, superclusters, voids. Above it, the universe smooths out, looking roughly the same in all directions. This transition from clumpy to smooth validates the cosmological principle and justifies treating the universe as a uniform fluid in cosmological models. The Cosmic Webb simulator projects like Illustrious and Eagle have reproduced the observed universe with stunning fidelity. Starting from initial conditions matching the cosmic microwave background, these simulations evolve billions of particles forward in time using the laws of physics. The resulting synthetic universes contain realistic galaxies, clusters, and voids that closely match observations. This success confirms that we understand the basic processes governing cosmic structure formation, even if mysteries like dark matter's identity remain. Lyman alpha blobs are enormous clouds of gas, sometimes spanning hundreds of thousands of light-years, glowing with hydrogen emission. Found in the distant universe when it was only 2 to 3 billion years old, these mysterious objects might be giant galaxies in formation, fueled by cold gas streaming inward along cosmic Webb filaments. Or they might be quasars whose light is scattering off surrounding gas clouds. Their nature remains debated, but they showcase the violent, energetic processes shaping galaxies during cosmic noon. Protoclusters, dense concentrations of galaxies in the early universe destined to become today's massive galaxy clusters, give us snapshots of cluster formation in progress. The James Webb Space Telescope has discovered some of the earliest protoclusters existing when the universe was less than 1 billion years old. These observations challenge our understanding of how structures could assemble so quickly, suggesting that the first seeds of clustering might have formed even earlier than we thought. The South Pole Telescope has discovered some of the most massive galaxy clusters in the universe through the Sunyaev-Zeldovich effect. This subtle distortion of cosmic microwave background photons passing through hot cluster gas allows astronomers to find clusters across enormous distances. Some clusters contain the mass of 1,000 trillion suns, representing the largest gravitationally bound structures in the universe. Their abundance tests our cosmological models because such massive objects should be rare. Cosmic noon, the peak epoch of star formation around 10 billion years ago, was also when supermassive black holes grew most rapidly. The relationship between star formation and black hole growth suggests deep connections between galaxy evolution and the monsters at their centers. Somehow, star formation in the galaxy disk feeds gas toward the center, fueling black hole growth, while black hole feedback eventually shuts down star formation. This cosmic dance shaped the galaxies we see today. The stellar mass function, the distribution of galaxies by their total stellar mass, has a characteristic shape across cosmic time. There are many low-mass galaxies and progressively fewer high-mass ones. This distribution reflects the interplay between gravity pulling matter together and feedback processes that blow gas out of galaxies. Understanding why the stellar mass function has its particular shape helps us comprehend the efficiency of galaxy formation across different mass scales. Cosmic downsizing refers to the surprising observation that massive galaxies form their stars earlier and more rapidly than smaller galaxies. This contradicts bottom-up structure formation, where small objects should form first and merge into larger ones. The resolution to this paradox is that massive galaxies assembled early from intense starbursts in multiple smaller galaxies, which then merge together while forming few new stars. So the dark matter halos grow bottom up, but the stellar populations form top down. Quenching, the process by which galaxies stop forming stars, remains one of galaxy evolution's central mysteries. Star formation can shut down rapidly over timescales of just a few 100 million years. Sometimes mergers trigger quenching, perhaps by disturbing the gas or feeding the central black hole. In other cases, galaxies seem to quench themselves as they age, perhaps running out of cold gas. Environment also matters. Galaxies in dense clusters quench more readily than isolated galaxies. The color magnitude diagram shows that galaxies divide into two populations, a blue cloud of star-forming galaxies and a red sequence of quiescent, non-star-forming galaxies. Understanding how galaxies transition from blue to red, crossing the sparsely populated Green Valley, is crucial for comprehending galaxy evolution. This transition involves quenching star formation, aging stellar populations, and possibly morphological transformation from spiral to elliptical shapes. Ultraluminous infrared galaxies, or ULIRGs, are cosmic dust factories producing stars at rates of hundreds of solar masses per year. These galaxies, often undergoing violent mergers, contain so much dust that they're nearly invisible in optical light, re-radiating absorbed starlight in the infrared. The most extreme examples produce stars 1,000 times faster than the Milky Way, burning through their gas reservoirs in just tens of millions of years. Submillimeter galaxies, discovered in the late 1990s, are dusty, star-forming galaxies in the distant universe. The Atacama Large Millimeter Array has revolutionized their study, revealing that many are massive galaxies forming stars at prodigious rates when the universe was only 2 to 4 billion years old. These cosmic dust clouds might be the ancestors of today's massive elliptical galaxies, having formed most of their stars in brief but intense bursts. The cosmic star formation history traces how the universe's overall star formation rate has changed over time. Star formation peaked at cosmic noon and has been declining ever since. The universe is slowly shutting down, converting its gas into stars ever more slowly. In the far future, star formation will essentially cease as galaxies exhaust their fuel. The universe's stellar populations will gradually redden as massive blue stars die and only long-lived red stars remain. The stellar initial mass function describes the distribution of stellar masses at birth. Remarkably, this function seems nearly universal. Galaxies across cosmic time and environment produce stars with similar mass distributions. Most stars are low-mass red dwarfs with progressively fewer intermediate mass and massive stars. This universality simplifies galaxy evolution models but also poses puzzles. Why should star formation produce the same mass distribution under such wildly different conditions? Population 3 stars, the universe's first generation born from pristine gas containing only hydrogen and helium, have never been directly observed. These hypothetical stars would have been massive, perhaps hundreds of times the Sun's mass, and incredibly hot, living fast and dying young in spectacular supernovae. Their explosions seeded space with the first heavy elements, enabling the formation of population 2 stars with trace metals. The James Webb Space Telescope searches for these cosmic pioneers, though detecting individual stars from 13 billion light-years away remains extraordinarily challenging. Globular clusters, dense spheres of hundreds of thousands of ancient stars, orbit galaxies like cosmic satellites. The Milky Way hosts about 150 globular clusters, some containing stars nearly as old as the universe itself. These stellar cities might be remnants of the first small galaxies that merged to build larger ones. Studying their ages, compositions, and orbits helps us reconstruct our galaxy's formation history and understand the building blocks from which it assembled. The galactic habitable zone considers where in the galaxy conditions favor planets that might support life. Too close to the galactic center and frequent supernovae bathe planets in deadly radiation. Too far out, and heavy elements necessary for rocky planets and life become scarce. Our solar system orbits in a sweet spot, far enough from the center to avoid frequent cataclysms, but close enough that our sun formed from sufficiently enriched gas. This cosmic real estate might influence where life can arise throughout the universe. Panspermia, the idea that life could spread between planets or even between star systems, becomes more plausible when we consider cosmic scales. Asteroid impacts can blast rock from planetary surfaces into space, potentially carrying dormant microbes. Within a galaxy, these fragments could drift for millions of years before landing on another world. If life arose once in a galaxy, it might spread to many worlds over billions of years, seeding the cosmos with biology. The universe's vast scales both isolate worlds and, paradoxically, connect them across time. As we've journeyed from our Milky Way to the cosmic horizon, one truth becomes inescapable: we are part of something incomprehensibly vast. Our galaxy, containing hundreds of billions of stars, is one among trillions spread across an observable universe 93 billion light-years across. Yet even this staggering volume represents only what we can see. The cosmic horizon beyond which light hasn't had time to reach us since the Big Bang. The numbers we've encountered, billions of galaxies, trillions of stars, light-years stretching across cosmic voids, are so large they lose meaning to our everyday minds. But here's what matters: you exist within this vast cosmic structure. The atoms in your body were forged in stars that died billions of years ago. The galaxy that birthed our sun formed from gas, enriched by countless previous generations of stars. You are, quite literally, the universe examining itself. When you look at the night sky, you're seeing across both space and time. Every photon entering your eye is a cosmic messenger carrying information from when and where it began its journey. The Andromeda galaxy appears as it was 2.5 million years ago, when our ancestors were just learning to craft stone tools. Distant quasars show us the universe's youth, when galaxies were still forming from primordial gas. Each observation is a glimpse into cosmic history, revealing how the universe evolved from the smooth, nearly featureless state after the Big Bang to the rich tapestry of structure we see today. The cosmic perspective transforms how we see ourselves. Yes, we're tiny, our planet a speck orbiting an ordinary star in the suburbs of an average galaxy, but we're also extraordinary. We're made of atoms, scattered by stellar explosions across light-years of space, gathered by gravity into a new solar system, assembled through billions of years of evolution into beings capable of comprehending the cosmos. We're the universe's way of knowing itself, conscious matter pondering its own existence. Our understanding of cosmic scales reveals both our insignificance and our significance. We're insignificant in size. A human compared to the observable universe is like a single atom compared to the entire Earth. But we're significant in capability. Through science and technology, we've mapped the cosmos from the Planck length to the cosmic horizon, understanding scales differing by 60 orders of magnitude. No other species we know of can claim this achievement. The fact that you can hold this knowledge, that you can comprehend the universe's vastness, even while being such a tiny part of it, is perhaps the most remarkable thing in existence. The universe is not just immense, it's comprehensible. The same laws of physics that govern atoms in your body also govern the formation of galaxies billions of light-years away. This unity, this cosmic consistency, allows us to understand our place in existence. Looking to the future, our observations will only improve. The James Webb Space Telescope will peer deeper into cosmic time, potentially glimpsing the universe's first stars. The Vera Rubin Observatory will map billions of galaxies, revealing the cosmic web in unprecedented detail. Gravitational wave observatories will open entirely new windows on the universe, detecting events invisible to light-based telescopes. Each new instrument expands our cosmic horizon, revealing phenomena we haven't yet imagined. But some horizons are absolute. The cosmic event horizon, created by accelerating expansion, marks regions we can never observe no matter how long we wait or how powerful our telescopes become. The observable universe is shrinking in a sense. More galaxies cross this horizon every day, disappearing from view forever as space expands between us faster than light can travel. We live in a special cosmic epoch when the universe is old enough to have formed complex structures, but young enough that we can still see its history written in distant galaxies. This makes our moment in cosmic history precious. Future civilizations, trillions of years from now, will see an emptier universe, only their local galaxy cluster visible against a vast darkness. They'll lack evidence for cosmic expansion, dark energy, or the Big Bang. We're fortunate to live when the universe reveals its secrets. This knowledge carries responsibility to preserve it, to build upon it, and to share it with all who wonder about our cosmic home. The question, how big is the universe compared to our galaxy, has no simple answer, because the universe might be infinite. But the observable universe, the sphere from which light has had time to reach us, is about 1,000,000 times wider than our galaxy. It contains at least 2 trillion galaxies, each with billions or trillions of stars. The total number of stars in the observable universe exceeds the number of grains of sand on all of Earth's beaches. And every one of those stars is a sun, potentially with planets, possibly with life, certainly with stories written in physics and chemistry. As you go about your life, remember that you carry the cosmos within you. The calcium strengthening your bones was created in exploding stars. The iron in your blood was forged in supernova cores. The oxygen you breathe was produced by massive stars that died before our sun was born. You are, in the most literal sense, children of the stars, pieces of the universe that have gained the ability to wonder, to question, and to understand. The next time you look up at the night sky, let yourself feel the immensity of what you're seeing. Those stars are nearby neighbors in our cosmic community. Behind them lie billions of galaxies, each an island universe containing its own billions of stars. And beyond our cosmic horizon, space and time continue, perhaps forever, filled with wonders we'll never see but can imagine. This is your inheritance as a human being, the knowledge that you're part of something vast, beyond comprehension, yet understandable through science. You're connected to every atom in the universe through a shared origin in the Big Bang. You're connected to every star through the elements they've created. You're connected to every galaxy through the cosmic web of gravity that binds all things together. If you made it through this entire cosmic reality check, you're exactly who I make these videos for. Subscribe for more mind-expanding journeys through space and time, and please give a thumbs up. If you enjoyed this video, I am sure you will love this other one at the left side of the screen. This is why we will never leave the Milky Way. Discover the real science behind our cosmic confinement and why intergalactic travel is impossible, not just for us, but for any civilization. See you there.